There are moments in astronomy when the scale of the universe hits you so hard it feels almost absurd. One such moment comes when you learn that somewhere out there drifts a spiral galaxy more than 5 times larger than our Milky Way, a structure so colossal that it stretches 522,000 light-years from end to end. This isn't a small margin of difference. This isn't just a bit bigger. This is the cosmic equivalent of looking at a familiar, bustling city and then being told that just beyond the horizon there exists a city so massive that it could swallow your own whole and still have space left over for 4 more just like it. The Milky Way, the very galaxy we call home, is already immense beyond human comprehension, about 100,000 light-years across. If you were to place our galaxy alongside this titanic neighbor, it would look like a child's toy beside a sprawling metropolis. The Condor Galaxy, formerly known as NGC 6872, doesn't just push the boundaries of what a spiral galaxy can be, it obliterates them. Its spiral arms reach so far into the dark, star-flecked abyss that even light, traveling at a blistering 300,000 kilometers per second, would take over 500,000 years just to cross from one edge to the other. And yet, this isn't some dim, faded relic of the past. The Condor Galaxy is alive with activity. Star nurseries flare at its edges, massive streams of interstellar dust sweep across its core, and its gravity commands the attention of smaller neighboring galaxies. In the vast, cold tapestry of the cosmos, it is a living giant, an astronomical apex predator of size and presence, gliding through the constellation Pavo like an enormous, celestial bird of prey. The name Condor feels poetic here, not just because of its wingspan-like spiral arms that appear to stretch out like feathers against the void, but because of the way it dominates the space around it, majestic, intimidating, and yet impossibly graceful. From our vantage point on Earth, this galactic titan is so far away that its light, the very photons hitting our telescopes, began their journey tens of millions of years ago, long before humanity existed, long before our ancestors even dreamt of the stars. When we look at it, we aren't seeing it as it is. We're seeing it as it was, frozen in a moment from a deep cosmic past. The sheer size of this galaxy raises countless questions. How does a spiral galaxy grow to such dimensions without losing its shape? What kind of cosmic events allowed it to evolve into something so far beyond the scale of most galaxies we know? What does it reveal about the life cycles of galaxies? And what does it tell us about the possible future of our own? Astronomers have studied the Condor Galaxy not just because it holds records, but because it represents an extreme case, an outlier that forces us to rethink the limits of galactic architecture. Its arms are not just long, they are drawn out to the point of distortion, their shapes influenced by gravitational interactions with other galaxies. Its core is not just bright, it is organized by a stellar bar structure that plays a critical role in how matter flows within it. And while its scale is daunting, its very existence invites one to consider the boundless creativity of the cosmos. If the Milky Way is the comforting home we know, the Condor Galaxy is the distant colossus that humbles us, a reminder that we live in a universe where large is a relative term, and where records are made to be shattered by forces older and more powerful than anything we can truly fathom. In the formal records of astronomy, this giant is listed simply as NGC 6872, a designation drawn from the New General Catalogue, a massive compilation of star clusters, nebulae, and galaxies assembled in the late 19th century by astronomer John Lewis Emile Dreyer. The number itself is nothing poetic. It's simply the sequence in which this object appears within the catalogue's methodical listing. It tells you nothing about the galaxy's appearance, its history, or its extraordinary scale. For most cosmic objects, that's where their story would end, an impersonal name tucked away in scientific databases, awaiting the attention of researchers. But NGC 6872 refused to remain anonymous for long. When astronomers first began capturing detailed images of it with modern telescopes, its shape leapt out immediately. From certain angles, the enormous spiral arms, stretched far wider than those of almost any known galaxy, looked uncannily like the outspread wings of a great bird soaring across the heavens. In those images, the elongated arms seemed to taper like feathers, while the central bar and bright nucleus resembled the robust body of a bird in flight. The resemblance was so striking that it earned a far more evocative nickname, the Condor Galaxy. The choice of condor wasn't accidental. The Andean condor, one of the largest flying birds on Earth, is famed for its vast wingspan and slow, majestic flight. Its image instantly conveys both power and grace, the same qualities embodied by this spiral titan drifting in deep space. In fact, when side-by-side comparisons were shown in popular astronomy circles, the metaphor became impossible to ignore. Here was a galaxy whose wings stretched 500,000 light-years, dwarfing even the largest spirals known, yet arranged in such a way that it seemed to glide effortlessly through the black sea of the cosmos. Nicknames like this serve an important purpose in astronomy. While catalogue designations are essential for precision, human beings connect more easily with imagery and metaphor. NGC 6872 might sound clinical, but Condor Galaxy invites the imagination to take flight. It makes the object not just a distant smear of light, catalogued by coordinates, but a vivid, living presence in our mental picture of the universe. That's why this galaxy is now far better known by its avian moniker than its formal code. The poetic name captures its soul, or at least the soul we project onto it. And as we move deeper into its story, that nickname will feel more and more appropriate, because the Condor Galaxy doesn't just resemble a bird in shape. In the grand theatre of space, it moves, interacts, and spreads its reach like a creature built to dominate the skies. The Condor Galaxy soars in a region of the sky that many casual stargazers rarely explore, the constellation Pavo, whose name means peacock in Latin. Pavo is a southern sky constellation, invisible to much of the northern hemisphere, which explains why NGC 6872 isn't a household name like Andromeda. To find it, you'd need to travel far south, to latitudes where the southern constellations wheel overhead in their nightly arc, revealing celestial wonders that northern observers never see with the naked eye. Pavo itself is a relatively modern constellation, introduced in the late 16th century by Dutch navigators Peter Dirkzoon Keyser and Frederick de Houtman during an age of maritime exploration when charting the southern skies became as important as mapping the seas. Nestled among other southern constellations like Indus and Telescopium, Pavo is not especially prominent in brightness, but it hides treasures that only telescopes can reveal, and NGC 6872 is its crown jewel. From our position on Earth, the light from the Condor Galaxy has traveled for about 212 million years before finally reaching our eyes and instruments. That means every image we take of it is a glimpse into an incredibly distant past. When the photons currently hitting our telescopes left the galaxy, dinosaurs had already been extinct for tens of millions of years. Mammals were diversifying across prehistoric Earth, and the continents were drifting toward the arrangement we know today. Humanity wasn't even a concept in the grand timeline. Our entire species would still be more than 200 million years away from existing. This vast distance isn't just a number to impress. It has profound implications for how we study the galaxy. Observing something 212 million light-years away means we are looking at an ancient snapshot, frozen in time. Whatever is happening in NGC 6872 right now, in this exact moment, is something we won't see for another 212 million years. In astronomy, that delay is unavoidable, and it turns every observation into a kind of time travel, letting us peer back into an era of the universe long before humans arrived on the scene. Locating the Condor Galaxy in the night sky requires precision because its faint light is easily drowned out by closer, brighter stars. From Earth, its position is roughly right ascension 20H 16 mir, and declination 70 degrees and 46, placing it deep within the southern celestial hemisphere. For professional astronomers, that position makes it an object best studied from observatories in the southern hemisphere, like those in Chile or Australia, where the galaxy passes high overhead. It's in these dark, dry, stable skies that instruments like the Very Large Telescope and other cutting-edge facilities can capture its sprawling form in exquisite detail. Even though it lies in an obscure part of the sky for most of the world, its remoteness doesn't diminish its majesty. In fact, there's something poetic about its position, far from the familiar constellations we can name offhand, hidden in a celestial southern wilderness, patiently waiting for human technology to evolve to the point where we could finally find it and appreciate its scale. And once we did, its presence in Pavo gave the constellation a new legacy. No longer just the peacock, but also the home of the largest barred spiral galaxy ever known. The size of the Condor Galaxy is so extraordinary that even astronomers, accustomed to dealing with unfathomable scales, pause when they talk about it. Measuring an astonishing 522,000 light-years from tip to tip, this barred spiral is more than 5 times larger than our own Milky Way. And when we say larger, we're not talking about some small difference you could glance over. This is the kind of size disparity that turns the Milky Way into a mere thumbnail against the Condor's panoramic spread. To put that into perspective, the Milky Way spans about 100,000 light-years across. If you could line up 5 Milky Ways edge to edge, you'd get something close to the length of the Condor Galaxy. But even then, you'd come up short by over 20,000 light-years. That's enough extra space to fit in another dwarf galaxy or two, just as a cosmic afterthought. If you replace the Milky Way with the Condor in the same location, its spiral arms would stretch far beyond the range of our local group's nearest neighbors. In fact, its edges might very well sweep past other galaxies entirely, intruding into regions of space we currently consider well beyond our home galaxy's influence. Visualizing this is challenging because the numbers quickly outstrip our intuition. Light travels at 300,000 kilometers per second, a speed so fast it can zip around Earth's equator more than 7 times in a single second. Yet even at that speed, light takes over 500,000 years to cross the Condor Galaxy's breadth. If you set off in the fastest spacecraft ever built by humans, traveling at a blistering tens of thousands of kilometers per hour, it wouldn't matter. You'd still need millions upon millions of years to traverse it. That means entire civilizations could rise and fall, and the journey from one end to the other still wouldn't be over. The Condor's enormous size is not just a statistic for record books. It fundamentally shapes its appearance, its behavior, and even its destiny. Spiral galaxies of this magnitude are rare because their size makes them structurally vulnerable. The larger the spiral disk, the more susceptible it is to gravitational disturbances, either from nearby galaxies or from internal processes like bar instabilities. Many massive galaxies eventually lose their well-defined spiral arms, evolving into elliptical galaxies over billions of years. The fact that the Condor Galaxy still retains a coherent barred spiral structure, despite its staggering proportions, is one of the reasons it fascinates astronomers. It's like finding a cathedral the size of a continent, still standing perfectly intact after centuries of earthquakes and storms. Part of the reason for its size lies in its cosmic history. Galaxies grow through mergers and accretion. They collide, absorb one another, and gradually pull in vast amounts of intergalactic gas and dust. In most cases, these mergers distort or destroy the spiral structure, but in certain rare conditions, the result can be a spiral galaxy that survives the interaction, only with greatly expanded arms. In the Condor's case, its size is likely the product of such interactions, including its ongoing gravitational dance with its smaller companion, IC 4970. These interactions can stretch a galaxy's arms outward, almost like taffy being pulled, increasing the overall diameter without tearing the spiral completely apart. If we could hover above the Condor Galaxy and look down on it from a bird's eye view, the immensity of its reach would be breathtaking. Its arms do not just curve gracefully around the core like those of a typical spiral. They sweep outward in great arcs that extend into the darkness, forming a kind of cosmic wingspan that seems too large to be stable. The outer edges are so far from the galactic center that the stars there orbit much more slowly, making the spiral pattern looser and more open compared to the tight, elegant coils of smaller galaxies like our own. This openness adds to the illusion of wings stretching in flight, and to the sense of fragility, as if one strong gravitational tug could send the whole structure unraveling into space. Another striking implication of its scale is the sheer number of stars it must contain. While exact estimates vary, a galaxy of this size could easily host several trillion stars, along with untold quantities of gas, dust, and dark matter. That's trillions of potential planetary systems, some perhaps with habitable worlds, all contained within one single galactic disk. In terms of potential for star formation and cosmic diversity, the Condor Galaxy is like a universe within a universe, offering countless regions where the processes of birth, evolution, and death play out on an astronomical stage. Astronomers often try to convey its size by comparing it to things we know. But the truth is, even these comparisons only scratch the surface. You could line up the Andromeda Galaxy, which itself dwarfs the Milky Way at about 220,000 light-years across, and the Condor would still double its span. You could stack entire chains of smaller galaxies, and they would still fall short. The Condor Galaxy doesn't just push the limits of spiral galaxy size, it resets the scale entirely, making giants like Andromeda suddenly seem modest. Perhaps the most humbling way to think about its size is to imagine standing on a planet near the very edge of one of its spiral arms. If you could look inward toward the galactic core, it might appear as a glowing mass of countless stars, stretching across the sky like a river of light. And if you could somehow see all the way to the opposite edge of the galaxy, it would be so far away that the light from those distant stars would have begun its journey before your world even existed. In a galaxy like this, distance takes on a whole new meaning. It becomes something almost eternal. The Condor Galaxy belongs to a class of galaxies that are both visually striking and structurally complex. It is a giant, barred spiral galaxy. That description might sound straightforward, but every word in it carries a world of meaning in astronomy. Giant sets it apart immediately, as spiral galaxies of this scale are rare. Spiral tells us about its distinctive arms, vast sweeping trails of stars, gas and dust that wind out from a central bulge. And barred describes the unusual feature that runs through its heart, a long, bright line of stars, like a cosmic bridge, stretching across the nucleus and anchoring the bases of the spiral arms. In the classification system astronomers use, barred spiral galaxies are denoted by the letter SB, for spiral barred. The Condor Galaxy, with its immense disk and prominent central bar, is a textbook, though extreme, example. In a standard spiral galaxy, like the Milky Way, spiral arms emerge more or less directly from the bulge at the center. In a barred spiral, however, these arms originate from the ends of the bar, which acts almost like a handle holding the arms in place. This structure isn't just a visual flourish, it plays a critical role in the galaxy's dynamics. Bars are believed to form due to instabilities in the rotating disk of stars and gas. Over time, the gravitational interactions between stars in the central regions can cause them to settle into elongated orbits, creating a bar-shaped distribution. This bar acts as a conveyor system, funneling gas from the outer regions toward the galaxy's core. The gas, drawn inward by the bar's gravitational influence, can ignite intense bursts of star formation near the center, and may even feed the supermassive black hole that most galaxies harbor at their hearts. In this way, the bar is both an aesthetic feature and a functional one, shaping the galaxy's evolution over billions of years. The Condor Galaxy's bar is particularly prominent because of its size and because of the gravitational interactions it's experienced with its companion galaxy, IC 4970. These interactions can enhance or elongate the bar, strengthening its grip over the galaxy's structure. In high-resolution images, the bar appears as a bright, elongated streak of densely packed stars, glowing more warmly than the blue-white star-forming regions in the spiral arms. This color difference comes from the fact that the bar is home to older, cooler stars, while the arms host younger, hotter, bluer stars born from fresh clouds of hydrogen gas. Beyond the bar, the Condor's spiral arms stretch out in grand arcs. Spiral arms are not static material like the arms of a windmill. Instead, they are density waves, regions where the concentration of stars and gas is higher, moving through the disk like ripples on a pond. As gas clouds enter these density waves, they get compressed, triggering star formation. This is why spiral arms shine so brightly with the blue light of young, massive stars. They're essentially cosmic nurseries. In the Condor Galaxy, these arms have been stretched to extraordinary lengths, and they appear somewhat distorted compared to those of smaller spirals. This distortion, caused largely by gravitational encounters, gives the galaxy a more open, wing-like appearance, enhancing the Condor imagery even further. The spiral structure of NGC 6872 is unusually open, meaning the arms do not wind tightly around the core, but instead sweep outward in broad curves. Astronomers refer to this as a low pitch angle. Such openness can be linked to a galaxy's size, rotation speed, and history of interactions. In the Condor's case, the openness may also be due to the tidal forces exerted by its smaller companion, which have pulled the arms outward over time. This has created a disk so vast and stretched that the galaxy's spiral nature is almost exaggerated, like a grand gesture frozen in the act of reaching. One of the most fascinating things about barred spirals is that they are not static structures. The bar itself can evolve over time. Simulations suggest that bars can form, dissolve, and reform over billions of years, depending on the galaxy's mass distribution and interactions. In the case of the Condor Galaxy, its immense size and the persistence of its bar suggest a long and possibly stable phase of barred structure, though given the constant gravitational tug-of-war with IC 4970, stability here is a relative term. The fact that such a massive galaxy retains its barred spiral identity is remarkable. Many galaxies of this size end up as giant ellipticals, amorphous, featureless collections of stars, because interactions and mergers erase their spiral patterns. The Condor Galaxy, on the other hand, remains a grand spiral despite its immense diameter, suggesting that it has managed to avoid the kind of catastrophic merger that would have completely restructured it. This makes it a valuable object of study, as it offers astronomers a chance to understand how spiral structure can endure even at extreme scales. When viewed in detail, the interplay between the bar and the arms becomes a kind of galactic choreography. The bar directs the flow of material inward, feeding the central regions, while the arms reach outward, capturing intergalactic gas and stars from beyond. Together, they sustain the life of the galaxy, a dynamic equilibrium that has persisted for hundreds of millions of years. In the Condor Galaxy, this dance happens on a stage so vast that our own Milky Way would be just a small prop in the corner. The Condor Galaxy's central stellar bar is one of its most striking and dynamic features. A vast, elongated structure composed of billions of stars, interstellar dust, and gas, stretching across its central region like a glittering cosmic bridge. This isn't just an aesthetic flourish in the galaxy's design. The bar is a fundamental engine of its internal evolution. It acts as both a conveyor belt and a sculptor, directing the flow of matter and shaping the galaxy's structure in ways that directly influence star formation, the growth of its central bulge, and the feeding of any supermassive black hole at its heart. The bar is essentially a gravitationally induced instability in the disk, a stellar wave that redistributes angular momentum and channels gas inward, allowing the galaxy to reorganize itself over time. In barred spiral galaxies, the stars and gas are not simply orbiting in neat circular paths. The gravitational pull of the bar creates elongated orbits for stars and acts as a gravitational handle that perturbs the galaxy's material. This distortion encourages gas clouds to lose angular momentum as they move along the bar's length, slowly spiraling inward toward the core. In the Condor Galaxy, the sheer scale of this feature magnifies its influence. It spans a significant portion of its already enormous disk, giving it the capacity to transport colossal amounts of gas from the spiral arms into the central regions. This is crucial for the galaxy's long-term vitality, as it delivers the raw materials necessary for intense starburst activity in the core. The bar also plays a critical role in fueling central star formation. As interstellar gas is funneled toward the center, it becomes compressed in dense pockets, triggering the collapse of gas clouds and the birth of massive clusters of stars. This process can ignite regions of intense starburst activity, where stars are born at rates far exceeding those in the outer disk. Such bursts are not only spectacular in luminosity, but also influential in shaping the galactic environment. They flood the surrounding regions with stellar winds, radiation, and eventually supernova explosions, which enrich the interstellar medium with heavier elements. In this way, the bar does not just transport matter, it seeds the conditions for the next generation of stellar life. In addition to feeding star formation, the bar's inward channeling of material can also contribute to the growth of the galaxy's central bulge. Over time, stars born near the center, along with redistributed older stars, accumulate into a more spheroidal distribution, changing the galaxy's overall morphology. The bulge may also conceal a supermassive black hole, and the influx of gas along the bar's gravitational pathways could serve as an intermittent food supply for it. If the black hole is active, this inflow can trigger episodes of quasar-like activity, where enormous amounts of energy are released as matter spirals into the event horizon. The existence of the bar in the Condor Galaxy is also linked to its gravitational interactions. NGC 6872's immense size and elongated arms suggest it has experienced past encounters with other galaxies, possibly the nearby lenticular galaxy IC 4970. Such interactions can amplify instabilities in the galactic disk, enhancing or even triggering the formation of the bar. As a result, the bar might be both a product of and a participant in the galaxy's ongoing dynamical evolution, responding to past tidal forces, while also reshaping the galaxy's internal flow of material. Interestingly, the bar doesn't just affect the central regions. Its gravitational influence extends outward into the spiral arms, organizing them into the sweeping, symmetric curves that define the galaxy's visual elegance. The material moving along these arms is subtly shepherded by the gravitational pull of the bar, helping maintain their cohesion over astronomical timescales. This interplay between the bar and arms gives the Condor Galaxy its majestic structure, while simultaneously ensuring that the central regions remain vibrant and active. From an observational perspective, studying the bar provides astrophysicists with a living laboratory to understand the mechanisms of secular galaxy evolution, those gradual processes that alter a galaxy's structure from within, independent of violent mergers or collisions. In the Condor Galaxy, the immense scale of the bar offers a magnified view of these dynamics, revealing how gravitational asymmetries shape the life cycle of stars and the redistribution of matter. Observations across multiple wavelengths, optical, infrared, and radio, show how stars dominate the visible length of the bar, while lanes of dust and gas run along its edges, tracing the inflow toward the center. The scale and efficiency of the Condor Galaxy's bar make it an exceptional example of nature's ability to engineer vast structures that act with precision on cosmic timescales. The bar's influence will likely persist for billions of years, gradually transforming the galaxy's appearance, feeding its central regions, and sustaining the processes that keep it alive with stellar activity. It is a reminder that, in the grand mechanics of the cosmos, beauty and function are inseparable. The shimmering stellar bridge is not only a masterpiece of galactic architecture, but also a critical artery in the life of one of the largest spiral galaxies ever observed. The spiral arms of the Condor Galaxy are nothing short of breathtaking in both scale and complexity, a sprawling set of cosmic highways that stretch across hundreds of thousands of light-years. These arms are not the neat, symmetrical structures we often associate with smaller and more orderly spiral galaxies like the Milky Way. Instead, they appear drawn out, warped, and twisted, almost as if some invisible force had reached across the galaxy and pulled them into elongated curves. This distortion is not random. It's the lingering result of gravitational interactions with neighboring galaxies, most notably a smaller companion galaxy that has been tugging at the Condor for millions of years. These gravitational encounters have stretched its arms far beyond what is typical, giving the Condor its remarkable 522,000 light-year size, which is more than 5 times the span of our own galaxy. If you were to stand on a hypothetical planet somewhere within one of these arms, you might look toward the galaxy's center and see it glowing faintly in the distance, while above and below you, other segments of the spiral arm would arc through the blackness like bridges of light suspended in the void. The arms themselves are littered with young blue stars that shine with a hot brilliance, evidence of intense star formation triggered by the same gravitational disturbances that twisted the galaxy's shape. Massive clouds of hydrogen gas trace the paths of these arms like neon outlines, fueling new stellar nurseries. Embedded within them are dense pockets of interstellar dust, which absorb and scatter light, creating dark lanes that run alongside brighter clusters of stars. These dusty regions are where gravity works most effectively, pulling matter together to ignite new stars. In smaller, more regular spirals, these processes happen in a relatively even and organized pattern. But in the Condor Galaxy, the disrupted structure means that some regions of the arms are overflowing with star-forming activity, while others are quieter, with vast stretches of dark emptiness separating clusters of brilliance. One of the most striking things about these elongated spiral arms is their sheer reach. They extend so far that if the Milky Way were placed at the Condor's center, our galaxy's outermost stars would barely reach halfway along one of its arms. The extreme length of these arms also means they are more susceptible to warping and fragmentation over time. Astronomers studying high-resolution images of the Condor have noted that the arms seem to taper into faint, thread-like streams toward their ends, almost dissolving into space. These faint streams may be remnants of tidal tails, vast rivers of stars and gas that were literally pulled out of the galaxy during close encounters with other galaxies in its past. Such tidal features are rare at this scale, making the Condor a valuable subject for studying the long-term effects of galactic interactions. The distorted shape of the spiral arms also tells a story about the galaxy's past motion and environment. The fact that the arms are not evenly spaced or uniformly bright suggests that the Condor has been in a dynamic, evolving state for millions of years. The smaller companion galaxy, IC 4970, plays a major role in this story. Located near one end of the Condor's elongated structure, IC 4970's gravitational pull is thought to have set off a chain reaction, compressing gas clouds in some regions, tearing others apart, and stretching the spiral arms into their current massive proportions. These distortions aren't fleeting. In the slow timescale of galactic evolution, they will persist for hundreds of millions of years before settling into a new form, if they settle at all, before another gravitational encounter reshapes them yet again. When viewed in different wavelengths of light, the arms reveal even more hidden details. In visible light, they showcase their bright blue star clusters and dust lanes, but in infrared, the dust becomes more transparent, revealing older, cooler stars hiding beneath the chaos of star formation. In radio wavelengths, astronomers can trace the distribution of hydrogen gas across the arms, mapping where future generations of stars might emerge. In ultraviolet, the youngest and hottest stars blaze even brighter, marking the regions where star formation is happening most fiercely. Each wavelength adds another layer to our understanding, painting a picture of a galaxy where the arms are not static decorations, but living, evolving structures constantly shaped by the forces around them. Perhaps one of the most awe-inspiring aspects of the Condor's spiral arms is the sense of motion they convey. Spiral arms are not fixed structures. They are more like patterns created by density waves moving through the galaxy. In the Condor, these density waves are exaggerated by the galaxy's massive size and the tidal forces acting on it. Over millions of years, stars will move in and out of the arms, gas clouds will be compressed into new stars, and old stars will drift away toward the outer regions. This constant recycling gives the arms a kind of heartbeat, a rhythm dictated by gravity, rotation, and cosmic interaction. And because the Condor rotates so slowly compared to smaller spirals, each cycle of this process is stretched out over vast spans of time, allowing astronomers to observe the effects in greater detail. If you were to zoom out and view the Condor from far beyond its boundaries, the elongated spiral arms would stand out like wings unfurling into the void, their asymmetrical arcs giving the galaxy its bird-like appearance and inspiring its name. The arms are not simply stretched, they seem to be reaching outward, as if the galaxy itself is trying to grasp at the space around it. This visual impression, combined with the scientific evidence of their formation, makes the spiral arms both a mystery and a testament to the dramatic consequences of galactic encounters. They are a frozen record of past cosmic events, and at the same time, an active participant in shaping the future of the galaxy. Even now, as astronomers continue to study the Condor, the full story of its spiral arms remains incomplete. Observations from advanced telescopes like the Hubble Space Telescope and the Atacama Large Millimeter Submillimeter Array, ALMA, have provided stunning detail, yet each new image raises fresh questions. How much longer will the arms remain in this distorted state? Will the companion galaxy eventually merge with the Condor, further twisting or even tearing apart these majestic structures? Or will the arms gradually relax back into a more balanced spiral pattern? Whatever the answers, the arms of the Condor Galaxy serve as one of the universe's grandest illustrations of both the beauty and the violence of galactic evolution. A reminder that even in the vast calm of space, colossal forces are constantly at work, reshaping the cosmos on a scale almost beyond comprehension. When looking deeper into the story of the Condor Galaxy, the presence of its smaller companion, IC 4970, cannot be ignored. This companion galaxy, much smaller in size but still an important cosmic player, has a gravitational relationship with the massive Condor that is both destructive and creative. IC 4970 sits relatively close to one of the Condor's spiral arms, and the two galaxies are currently in a stage of interaction that astronomers suspect has been unfolding for hundreds of millions of years. Their gravitational dance is the reason the Condor Galaxy structure looks as unusual and stretched as it does today. In fact, without IC 4970's influence, the Condor may have retained a far more symmetrical, classic barred spiral appearance. Instead, what we see now is a massive spiral galaxy with arms that are warped, elongated, and in some areas thickened due to tidal forces. These tidal forces occur because the gravitational pull of IC 4970 is not uniform across the Condor Galaxy structure. Parts of the Condor closer to IC 4970 are pulled slightly more strongly than those farther away, and this difference distorts the Condor's spiral arms and central disk. Gas, dust, and even entire star clusters in the Condor are nudged out of their original orbits, setting off waves of compression in the interstellar medium. These compression waves can trigger bursts of star formation, especially in the regions where the spiral arms have been drawn out into vast, delicate streams of material. This means that IC 4970, while technically disrupting the Condor Galaxy, is also partially responsible for creating bright new star clusters that light up parts of the arms. The gravitational interaction also works both ways. IC 4970 is being affected too. Although its smaller size means it can't warp the Condor to the same extreme degree that the Condor could theoretically warp it, its own structure is likely being influenced. IC 4970's outer layers may be stripped of gas over time, and streams of material may even be siphoned off into the Condor Galaxy. Over long cosmic timescales, this process can lead to the complete merger of the two galaxies, especially if their orbital paths continue to bring them closer together. When such a merger happens, IC 4970 will essentially become part of the Condor's structure, contributing its stars, gas, and dark matter to the much larger galactic body. Astronomers suspect that this interaction began when IC 4970 passed close to the Condor Galaxy for the first time, perhaps hundreds of millions of years ago. That initial pass would have set off large gravitational ripples, bending and twisting the Condor's arms and causing its bar to channel even more material toward the center. Each subsequent pass would deepen the distortions, and because galaxies move at immense speeds relative to one another, but are also bound by gravity, these encounters are not quick affairs. They play out over hundreds of millions of years. In the case of the Condor Galaxy, the interaction has reached a stage where its arms are visibly asymmetric. One side appears to stretch farther and curve more loosely than the other, as if one wing of the Condor is extended outwards while the other is more tightly folded in. This lopsided appearance is one of the features that makes the galaxy so recognizable in deep space images. There is also the question of how IC 4970's presence impacts the Condor's future evolution. Galaxies are not static objects. Their appearances change drastically over time due to mergers, internal dynamics, and environmental factors. In the coming hundreds of millions of years, the Condor may either settle into a new shape after IC 4970 drifts away, or, more likely, absorb the smaller galaxy entirely. If a merger occurs, the central bar could become even more prominent. New waves of star formation could erupt across the arms, and the overall brightness of the galaxy might increase for a time. But eventually, as star formation slows and older stars dominate, the galaxy could take on a more elliptical appearance, losing its beautiful spiral structure altogether. This is a fate that has befallen many spirals after major mergers. From an observational standpoint, IC 4970 also serves as a cosmic clue, telling astronomers about the Condor's past encounters. By studying the velocity and motion of both galaxies, scientists can trace backward in time to reconstruct the gravitational paths that brought them together. Computer simulations allow researchers to model different collision scenarios, matching them to the distortions we see today. These simulations suggest that the Condor's immense size and extended arms may have been enhanced by previous mergers before IC 4970 came along, and that this current interaction is only the latest chapter in a much longer history of galactic evolution. This relationship between the two galaxies is also a microcosm of the larger processes shaping the universe. Galactic interactions are a primary driver of change in the cosmos, responsible for both destruction and creation. They can strip galaxies of their raw material, starving them of the gas needed to make new stars, but they can also ignite spectacular bursts of starbirth by compressing interstellar gas clouds. The Condor and IC 4970 are therefore an excellent example of the dual nature of cosmic evolution, how beauty and chaos, order and disorder, are intertwined in the universe's grand design. Seen in high-resolution space telescope images, the contrast between the Condor Galaxy's massive, sprawling form and the much smaller, darker IC 4970 is striking. The companion galaxy appears as a small, compact oval shape, with little obvious structure, compared to the vast, feathered sweep of the Condor's arms. This size difference emphasizes just how colossal the Condor really is. It spans over 522,000 light-years, more than 5 times the diameter of the Milky Way, while IC 4970 is only a fraction of that. Yet despite its size, IC 4970's gravitational influence is undeniable, a reminder that in the realm of galaxies, mass and distance play a far greater role than sheer size in determining the outcome of these interactions. In the cosmic dance between the Condor Galaxy and IC 4970, we are witnessing a living snapshot of galactic evolution in progress, a process that takes place on timescales far beyond a human lifetime, yet leaves visible marks that we can study today. It's a slow-motion ballet of gravitational attraction, material exchange, and structural transformation. The distorted arms, the heightened star formation, and the subtle changes in both galaxies' trajectories all speak to the invisible threads of gravity weaving their fate together. While the Condor Galaxy would already be a spectacular sight on its own, the presence of IC 4970 makes it not just a static wonder, but a dynamic and evolving masterpiece of the universe. When the Condor Galaxy's immense spiral structure is examined, its extraordinary arms, extending more than 500,000 light-years from end to end, immediately reveal a story written not by quiet, isolated evolution, but by the gravitational turmoil of a close cosmic encounter. This encounter is the root of the galaxy's extraordinary elongation, and it is driven by one of the most dramatic processes in galactic dynamics: tidal forces. These are not the gentle tides we associate with the Moon pulling on Earth's oceans, but vast, unrelenting distortions of matter on a scale so immense that entire clouds of stars, gas, and dust are dragged from their original orbits. In the Condor's case, the culprit is its smaller companion, IC 4970, which passed close enough to set off a gravitational chain reaction that has shaped every spectacular curve and extension of the galaxy's form. To understand how the Condor's arms became so impossibly stretched, it helps to visualize the gravitational tug-of-war that occurs during galaxy interactions. Every star, planet, gas cloud, and dust particle in a galaxy is bound to the system's gravitational center, orbiting under the influence of the galaxy's mass. But when another galaxy drifts too close, its own gravitational field pulls unevenly across the larger galaxy. The side of the Condor closest to IC 4970 felt a stronger pull than the far side, just as the near side of Earth feels the Moon's gravity more strongly than the far side. This imbalance sets up tidal forces, differences in gravitational pull across the galaxy, that can literally stretch the stellar disk into new shapes. In the Condor's specific case, these tidal forces worked along its disk's plane, yanking stars outward along the spiral arms. At the same time, the motion of the intruding galaxy stirred up the Condor's rotational pattern, amplifying the winding of its spirals and exaggerating their length. The result is the visual signature we see today: arms so elongated and slender they resemble the wings of a colossal bird in flight. In fact, this avian resemblance is the reason astronomers gave it its informal name, as if the galaxy itself is soaring through intergalactic space with wings spread wide. But tidal stretching is more than just an aesthetic transformation. It physically redistributes the galaxy's matter in dramatic ways. Huge arcs of stars are flung outward into faint tidal tails, their orbits altered permanently. Gas clouds, once in stable rotation, are shoved into new positions where they may collapse under their own weight, triggering bursts of star formation. These processes are happening now in the Condor, as evidenced by bright blue knots embedded in its arms, newborn star clusters ignited by the compression of interstellar gas during the stretching. This dual process of stretching and starburst activity is common in interacting galaxies, but the Condor takes it to an extreme because of its sheer size and the specific geometry of the encounter. The angle and speed at which IC 4970 passed by the Condor played a decisive role in shaping this outcome. A glancing, off-center approach meant the gravitational pull was asymmetrical, with one spiral arm experiencing a stronger outward draw than the other. This asymmetry amplified the Condor's already impressive size, giving one arm a reach of nearly twice the Milky Way's entire diameter. Simulations of similar galaxy encounters show that these elongated arms are transient. Over the next few 100 million years, the arms will likely wind back inward, fragment into streams of stars, or merge into a new galactic shape altogether. For now, though, the Condor is caught in this rare photogenic phase, where its spiral arms appear impossibly stretched and graceful. The tidal forces at work are not limited to reshaping the spiral pattern. They also disrupt the orbits of stars within the central bar of the galaxy. In barred spirals like the Condor, the bar channels gas toward the core, fueling both star formation and possibly feeding a central black hole. When tidal forces act on the bar, they can strengthen it temporarily, creating even more efficient channels for gas inflow. This could be why the Condor shows signs of enhanced central activity. Though not to the extreme of a quasar or active galactic nucleus, there is evidence that the tidal encounter has stirred its heart into a livelier state. Perhaps the most fascinating aspect of tidal stretching in the Condor is how delicately balanced the process is between destruction and creation. On one hand, the gravitational pull of IC 4970 has thrown the galaxy into chaos, distorting its arms and scattering its stellar population. On the other hand, that very chaos is breathing new life into the system, sparking waves of star formation and reshaping the galaxy into something visually unparalleled. Over cosmic time, this balance will tip. If the two galaxies merge, the Condor's iconic wings will vanish, replaced by a more amorphous, elliptical structure. For now, however, the Condor exists in a fleeting window of beauty, with its tidal forces having stretched it into a record-breaking giant. Astronomers have long used galaxies like the Condor as natural laboratories to study tidal forces because the effects are so visible and exaggerated. Observations in different wavelengths, optical, infrared, and radio, reveal the full story. Optical images show the brilliant arcs of stars in the arms. Infrared views highlight the warm glow of dust heated by newborn stars. And radio maps trace cold hydrogen gas drawn far from the core by tidal forces. In the Condor, these data sets line up perfectly with the expected patterns from a strong tidal interaction, confirming that the spectacular elongation is not just a quirk of perspective, but the real, physical stretching of a galactic disk on a scale that defies ordinary expectations. What makes the Condor's case even more captivating is that it's still evolving. The tidal forces that created its current form are ongoing, subtly changing the positions of stars, compressing clouds of gas, and altering the orbits of material far from the galactic center. Every observation of it is essentially a snapshot in a grand, slow-motion ballet between two galaxies, one that began hundreds of millions of years ago and will continue for millions more. It is a reminder that even on the grandest scales, cosmic beauty is often born from gravitational conflict, and that the Condor's immense wingspan is a testament to the quiet but relentless power of tidal forces shaping the universe. The Condor's immense spiral arms, stretched to extraordinary lengths by gravitational interactions, are not just barren streams of stars. They are alive with cosmic activity. At the farthest reaches of these arms, especially near the tips, lie clusters of intense blue light. These are star formation hotspots, regions where enormous clouds of gas have been compressed to the point of collapse, igniting the birth of countless young, massive stars. The brilliant blue color is not accidental. It comes from these massive newborn stars, many of them several times the size of our Sun, blazing fiercely at temperatures of tens of thousands of degrees. Such stars burn hot, shine intensely in the blue and ultraviolet part of the spectrum, and live short but spectacular lives. Their radiation pours into the surrounding space, energizing and illuminating the very clouds that created them. These hotspots are the direct consequence of the Condor's turbulent history. The gravitational pull from its smaller galactic companion hasn't just stretched the spiral arms, it has set off shockwaves through the interstellar medium. These shockwaves compress hydrogen gas in the arm's outskirts, triggering the collapse of molecular clouds. In galaxies, star formation is often strongest where forces converge, spiral density waves, tidal shocks, or colliding gas streams. And in the Condor, all three have been at play. The result is a cosmic laboratory for studying how interactions shape stellar nurseries. Observations in optical and ultraviolet light reveal bright, compact regions glowing intensely at the arm tips, each teeming with hundreds of thousands, if not millions, of young stars. The sheer distance of these star-forming regions from the galaxy's core is also extraordinary. In most spiral galaxies, such hotspots are concentrated toward the inner arms or along the bar structure. But in the Condor, they are flung out to regions hundreds of thousands of light years from the galactic center, so far that if they were separated from the galaxy, they might appear as small, faint dwarf galaxies in their own right. This is part of what makes the Condor's outer arms so remarkable. They are both a structural anomaly and an active zone of starbirth, a rare combination that offers astronomers a glimpse into processes that may have been common in the chaotic early universe when galaxies were colliding more frequently. When viewed through space telescopes, these bright blue knots at the arm tips are not isolated. Many are connected by faint streams of stars and dust, evidence of the tidal bridge and tail structures sculpted by the collision. The knots themselves are embedded in regions rich in hydrogen gas, detected via radio observations, which confirms that these are genuine stellar nurseries, not merely old star clusters drifting in the outskirts. The blue light we see is also fleeting. In astronomical terms, these hot young stars will only shine for a few million years before exhausting their fuel and ending their lives in powerful supernovae. Each supernova will then seed its surroundings with heavy elements, enriching the gas for future generations of stars, and perhaps even triggering further waves of star formation. The fact that the Condor's star formation hotspots are located so far from the galactic center raises intriguing questions. How long will they remain gravitationally bound to the galaxy? Will they eventually drift away, forming satellite dwarf galaxies? Or will the Condor's gravity pull them back inward, folding the elongated arms into a more compact spiral shape over the next few billion years? These questions aren't just academic. They touch on the very nature of galaxy evolution. Simulations of galactic collisions suggest that such extended star-forming regions can either be reabsorbed or, in cases of extreme tidal stretching, torn away entirely to become independent systems. There is also the possibility that some of these star-forming hotspots could merge with other small galaxies or gas clouds in the future, adding yet another layer of complexity to the Condor's already turbulent history. If this happens, the outer arms might see multiple generations of star formation, creating stellar populations with varying ages, metallicities, and spatial distributions. Astronomers studying the Condor with multi-wavelength observations, from radio arrays mapping cold gas to ultraviolet telescopes capturing the youngest stars, are piecing together this stellar genealogy, hoping to understand how such extended and active arms can persist for so long after a collision. From a visual standpoint, these regions add a striking beauty to the Condor's already awe-inspiring form. The galaxy's vast wings of starlight stretch outward like a cosmic albatross, with the brilliant blue tips serving as beacons at the ends of each wing. In deep, high-resolution images, you can trace the faint, curving streams of stars that connect the hotspots to the inner structure, giving the impression of a galaxy mid-flight, scattering new stars into the darkness of intergalactic space. This interplay of form and function, structure shaped by tides, activity fueled by compression, makes the Condor a perfect example of how violence in the cosmos can give rise to extraordinary beauty. The existence of such vibrant star formation at such remote distances from the core also suggests that the Condor has access to a surprisingly large reservoir of cold gas, far beyond the usual limits of spiral galaxies. This gas may have been stripped from its smaller companion during the collision, or it could be primordial material that has lingered in its outer halo since its formation. Either way, its presence ensures that the outer arms can remain active for many millions of years to come. As time passes, the balance between star formation and gravitational reconfiguration will decide whether the Condor retains its record-breaking size or gradually settles into a more conventional spiral form. For now, these star-forming hotspots stand as a vivid testament to the galaxy's ongoing evolution. They show that even in the aftermath of disruptive gravitational encounters, a galaxy can thrive, not just surviving the chaos, but using it to forge something new. In the Condor's case, the collision hasn't merely stretched its arms to the point of record-breaking length. It has sparked a cosmic fireworks show at the very edges of its domain, turning the galaxy into both a monument to tidal forces and a cradle for newborn stars. While the Condor Galaxy's spectacular blue knots at the tips of its arms are evidence of intense, ongoing starbirth, the story changes dramatically as your gaze shifts inward toward the heart of the galaxy. Here, the scene is painted in a very different light, literally. Instead of the piercing, energetic blue hues of young, massive stars, the central regions glow with a warmer, reddish tone. This is the signature of older stellar populations, stars that have long since passed the feverish pace of their youth and settled into quieter, cooler stages of their lives. These central stars are often small to medium in size. Many are yellow and red giants, or even long-lived, low-mass red dwarfs that have been shining steadily for billions of years. Their combined light creates a softer, amber-like glow, giving the galactic core a sense of age and stability in contrast to the dynamic chaos of the outer arms. This reddish central region acts like a living record book of the Condor's past, while the star-forming regions on the galaxy's periphery tell of a recent era of interaction and gravitational disruption. The stars in the core whisper of a much earlier chapter. Many of them formed when the galaxy was still relatively young and untouched by the dramatic collision with IC 4970. Their orbits are more stable, their lives longer, and their energy outputs more modest than the massive, short-lived stars blazing out on the galactic frontier. These older stars collectively suggest that the Condor Galaxy's central bulge has likely remained intact through countless smaller cosmic events, weathering both the internal turbulence of its own spiral structure and the external nudges from neighboring galaxies. Astronomers study these reddish regions because they act as a sort of galactic fossil record. By analyzing the light coming from them through a technique called spectroscopy, they can determine the age distributions, chemical compositions, and metallicities of these stars. High metallicity in the core stars often points to a history of repeated generations of stellar birth and death, with supernova enriching the surrounding gas over billions of years. In the case of the Condor, such data can reveal how its evolutionary path unfolded long before the dramatic stretching of its arms began. It's also worth noting that older stellar populations tend to cluster more densely toward the center due to the gravitational pull of the galactic bulge and possibly a central supermassive black hole. While the Condor's core has not been studied as extensively as some other nearby galaxies, it is plausible, based on patterns seen in similar spirals, that a massive black hole lies at its center, anchoring these stars in stable, elliptical orbits. These tightly bound orbits create a contrast in motion when compared to the more chaotic and sometimes irregular paths of stars in the outer disk, especially in a galaxy undergoing tidal stretching. Interestingly, the reddish hue of the central regions is not just about stellar age, it's also about the absence of fresh gas. Star formation requires cold, dense clouds of hydrogen, but over time, much of the gas in a galaxy's core can be consumed, blown away by stellar winds, or heated by the activity of the central black hole, if one is present, making it unavailable for forming new stars. Without that fuel, the region becomes dominated by older stars, as no new, bright blue ones can emerge to replace them. This creates a natural visual transition from the blue star-forming outskirts to the red, settled heart of the galaxy. In the Condor Galaxy, the juxtaposition of these two stellar populations is striking. It's as if you're looking at two different epochs of cosmic history, frozen side by side. The outer arms, flaring with youthful energy, are like the fresh ink of a story still being written, while the central bulge is the faded parchment of ancient chapters, its words etched deep into the structure of the galaxy. This duality also underscores how galaxy interactions like the one with IC 4970 can be selective in their influence. The outer arms are violently reshaped and ignited into new life, but the core remains largely untouched, its ancient stars continuing their slow, steady evolution. The reddish light spilling from these older stars has traveled millions of years to reach us, meaning we see the Condor's heart as it was in a snapshot long before humanity existed. Every photon is a messenger from an older, quieter universe, one in which the galaxy was already mature, but still destined for the dramatic transformation we observe today. These inner stars bear silent witness to both the endurance and fragility of galactic structures. Endurance, because they have survived for eons in stable orbits. Fragility, because their fate is ultimately tied to the larger forces shaping the galaxy as a whole. This contrast between the galaxy's blue extremities and its red core doesn't just make the Condor a feast for the eyes. It makes it a layered, dynamic archive of cosmic evolution. The same gravitational encounter that drew out its wings and lit up the star-forming tips has also left the central bulge largely undisturbed, allowing these ancient stars to remain as they have for ages. They stand as a reminder that even amid the most spectacular cosmic upheavals, parts of a galaxy can carry on almost serenely, holding fast to the light of bygone eras, while the outskirts dance to the chaotic tune of change. In the vast expanse of the Condor Galaxy, one of its most defining and life-sustaining traits lies in its immense reserves of hydrogen gas and interstellar dust, the raw ingredients for building stars, planets, and ultimately, the complex structures we associate with galaxies teeming with activity. These reservoirs are not merely passive components drifting quietly through space. They are the dynamic lifeblood of the galaxy's ongoing evolution, feeding the stellar nurseries that dot its spiral arms and ensuring that the process of creation never truly halts. Hydrogen, the simplest and most abundant element in the universe, plays the starring role in this story. In the Condor Galaxy, enormous clouds of this element span thousands of light years, forming vast, diffuse nebulae that stretch along the galaxy's intricate arms. Some regions are dominated by cold hydrogen gas, largely invisible to the naked eye, but detectable through radio wavelengths, where astronomers can trace its sprawling, delicate outlines. Other pockets of hydrogen are energized by nearby newborn stars, glowing brightly in the telltale pinkish-red light of hydrogen alpha emission, betraying the locations of fierce stellar birth. These clouds of gas are rarely pristine. They are threaded with fine particles of dust, tiny solid grains composed of heavier elements such as carbon, silicon, and iron. Though they make up only a small fraction of the galaxy's total mass, these dust grains are critical to the cycle of star formation. They help cool the surrounding gas, allowing it to collapse under its own gravity into dense clumps where new stars can ignite. The dust also plays a more subtle role, shielding delicate molecular clouds from harsh ultraviolet radiation that could otherwise tear them apart before they have a chance to form stars. In the Condor Galaxy, these dust lanes are often seen as dark, intricate filigrees cutting across the brighter glow of starlight, delicate shadows that mark the locations of unseen stellar nurseries preparing to burst into life. The sheer quantity of this raw material in the Condor Galaxy is extraordinary. Measurements indicate that it possesses one of the richest gas and dust supplies among known spiral galaxies, a likely consequence of its immense size and the gravitational interactions it has experienced over time. Encounters with neighboring galaxies have not only stirred its structure, but also funneled fresh material into its arms, replenishing the reservoirs needed for star formation. This continuous supply ensures that even though stars are constantly being born and dying, the galaxy's star-making engine remains fueled and active. The process is self-sustaining to a degree, as massive stars, once they reach the ends of their short but brilliant lives, explode as supernovae, scattering heavy elements and shockwaves back into the interstellar medium. These shockwaves compress nearby clouds of gas, triggering the next round of star formation in a cosmic feedback loop that has been running for billions of years. From a distance, these regions of concentrated gas and dust are what give the Condor Galaxy its intricate, patchy texture. The dust obscures some starlight while reflecting and scattering light from others, creating areas that shimmer in soft, muted tones. When combined with the sprawling blue arms, lit by young stars, and the warmer glow of older stars near the center, the result is a galaxy that seems to pulse with life, its very structure shaped by the interplay between gas, dust, and gravity. Astronomers study these regions not only to understand the Condor Galaxy itself, but also to gain insights into the universal process of galactic evolution. The physics governing the collapse of gas clouds, the birth of stars, and the dispersal of material is largely the same across the cosmos, meaning the Condor offers a spectacularly scaled-up laboratory for studying these processes in exquisite detail. Dust, despite its small-scale structure, has an outsized effect on how we perceive the galaxy. It absorbs and re-emits starlight in the infrared part of the spectrum, meaning that while some of its most vibrant regions might appear faint or hidden in visible light, they glow brilliantly in infrared observations. This reveals pockets of intense star formation that would otherwise remain cloaked. The Condor Galaxy's vast dust lanes also offer a historical record of its dynamic past. Warps, twists, and irregular patterns hint at gravitational disturbances, mergers, or close passes with other galaxies that have redistributed its material over millions of years. In this way, the dust is not just a participant in the galaxy's growth, but also a witness to its history. The hydrogen gas, too, tells a story. By mapping the velocity and distribution of the gas, astronomers can trace the rotation of the galaxy, identify regions where material is being compressed, and even detect signs of past encounters with other galactic systems. In some areas, gas flows along tidal bridges, faint connections of material stretching toward neighboring galaxies, suggesting that the Condor has not evolved in isolation. These interactions often act as a catalyst for starbursts, where star formation rates spike dramatically as gas is funneled into dense, active regions. Given the Condor Galaxy's remarkable span of over 500,000 light-years, the scale of these star-forming complexes is immense, with some stretching for thousands of light-years and producing tens of thousands of new stars in a single burst. Perhaps the most awe-inspiring aspect of this interplay between gas and dust is its role in shaping the galaxy's long-term destiny. While stars will eventually burn out and die, returning much of their material to the interstellar medium, the overall supply of hydrogen will gradually diminish over billions of years. As the fuel runs low, the Condor Galaxy's vibrant blue arms will fade, its star formation will slow, and it will transition into a quieter, more sedate phase of existence, much like the older, redder galaxies we see today. But for now, in this era of abundance, the galaxy thrives in a state of constant renewal, a cosmic engine fueled by the simplest element in the universe, building structures of unimaginable complexity and beauty from clouds of gas and specks of dust drifting in the dark. The Condor Galaxy does not exist in isolation. Like most galaxies in the cosmos, it is part of a much larger cosmic neighborhood, surrounded by other galaxies, clusters, and vast structures that help shape its story. While it is the largest spiral galaxy known, stretching over 500,000 light-years. Its immense arms extend into an environment populated with other significant celestial bodies. The most notable neighbor to the Condor Galaxy is IC 4970, a smaller, lenticular galaxy that has been in close gravitational interaction with it for hundreds of millions of years. This companion is not just passively drifting nearby. It has likely been one of the key drivers behind the Condor's stretched, distorted, and elongated spiral arms. Astronomers believe that past close passes between the two galaxies stirred up massive gravitational tides within the Condor, triggering waves of star formation and pulling streams of gas and dust outward, creating some of the longest arms ever observed in a spiral galaxy. The influence of IC 4970 can be seen in the way certain parts of the Condor's arms are warped, with dense knots of blue light marking stellar nurseries that have been set ablaze by these gravitational encounters. This interaction is still ongoing, though not as violent as a direct collision. Over cosmic timescales, the smaller galaxy may eventually merge with the Condor, contributing its stars, gas, and dark matter to the already massive spiral. But IC 4970 is not the only resident of this cosmic address. The Condor Galaxy lies within the Pavo constellation, a region of the southern sky rich in deep space structures. Nearby, there are other spiral galaxies, some barred and some irregular, scattered like islands in a dark ocean, each with their own complex histories of mergers, star births, and quiescent phases. These galaxies are all part of a loose group, or possibly a larger-scale filament that feeds into the vast web of the universe. This cosmic web is composed of immense filaments of galaxies stretching for hundreds of millions of light-years, separated by enormous voids that contain almost nothing. In this network, the Condor and its neighbors are like beads on a string, held together by the invisible grip of dark matter. The gravitational pull between them can subtly alter their motions, cause future encounters, and set the stage for additional bursts of star formation or even full-scale mergers. On a larger scale still, the Condor's region lies within a supercluster environment, though it is far from the dense, bustling hubs like the Coma or Virgo clusters. Instead, its home is more spread out, with galaxies spaced at greater distances, allowing giants like the Condor to retain their extended spiral structures without being torn apart by the intense gravitational harassment seen in richer clusters. This relative isolation might be one reason why the Condor could grow to such immense proportions, avoiding frequent destructive encounters that tend to shrink or transform other spirals into elliptical galaxies. Beyond the galaxies visible in its immediate vicinity, there are also many dwarf galaxies in the region. These smaller systems, faint and often irregular in shape, orbit larger galaxies like satellites. While none have been directly confirmed to be bound to the Condor in the same way the Magellanic Clouds orbit the Milky Way, it is very likely that faint companions do exist, given its mass and gravitational reach. These dwarfs could serve as fuel depots for the Condor's future growth, their gas-rich contents slowly drawn in over billions of years, sparking new rounds of star formation. The intergalactic space around the Condor is not empty either. It is threaded with tenuous streams of hydrogen gas, remnants of past interactions, and possibly the stripped material of smaller galaxies that passed too close. These gas flows are part of the larger intergalactic medium, a vast and faintly glowing network of matter that connects galaxies. This medium can act as both a source and a sink for the Condor's material, sometimes feeding it fresh gas, other times stealing it away through gravitational and tidal forces. Farther afield, there are also massive elliptical galaxies in the region, ancient systems that have already undergone their most active periods of star formation and now shine with the steady light of older, redder stars. These giants are relics of a different type of galactic evolution, often products of repeated mergers over the eons. They serve as a quiet contrast to the sprawling, active arms of the Condor, showing the diversity of galactic life even within the same cosmic neighborhood. The Condor's setting in the universe offers astronomers a laboratory for studying the interplay between galaxies. By observing not just the Condor itself, but the galaxies and structures around it, scientists can trace the invisible gravitational scaffolding that shapes the cosmic landscape. It also allows them to see how environmental factors influence the growth, star formation, and morphology of such an enormous spiral. The fact that the Condor resides in a relatively open, less crowded galactic neighborhood may have been a key factor in allowing it to achieve and maintain its extraordinary size, while still engaging in the occasional gravitational dance with its smaller companions. In a way, the Condor's neighborhood reflects a delicate balance, close enough to other galaxies to spark new star formation through interactions, but not so crowded that it risks being violently transformed or stripped bare. Over the next several billion years, this balance will shift. IC 4970 may merge into the Condor, other dwarfs might be captured, and distant neighbors could drift closer, all slowly reshaping this giant. Yet for now, it remains the undisputed monarch of its local region, a cosmic titan presiding over a court of smaller galaxies, each bound by the threads of gravity in an endless celestial tapestry. When the galaxy now known as NGC 6872, later nicknamed the Condor Galaxy, was first catalogued, it was in an era when astronomers were still grappling with the full scale of the universe beyond our own Milky Way. Its entry into the astronomical record came in the late 19th century, during the great age of systematic sky surveys in the southern hemisphere. At that time, many prominent observatories were working to map the heavens in detail, and the southern skies, rich with exotic targets invisible from Europe or North America, were a particular focus. This vast spiral was first noted as a faint, elongated smudge of light through the eyepieces of some of the most powerful refractors and early reflectors of the day. The true nature of such nebulae was still under debate. Many astronomers assumed they were clouds within the Milky Way, since the concept of island universes was still gaining traction. In early catalogue records, its immense size was entirely unsuspected. From the limited resolution of the period, it appeared only as a stretched oval patch, with no hint that it was a barred spiral on a truly staggering scale. As photography began to replace visual observation in the late 19th and early 20th centuries, astronomers obtained their first long-exposure plates of the object, revealing more structure than could be discerned by eye. Even then, the galaxy's delicate, elongated arms were only faintly visible, and only with extended exposures that pushed the limits of the emulsion's sensitivity. It was during the mid-20th century, with the advance of large aperture telescopes like those at the Cerro Tololo Inter-American Observatory in Chile, that its grandeur began to emerge more clearly. Observers began to recognize that this was not a modest-sized spiral, but one of truly outsized proportions, stretching hundreds of thousands of light-years from end to end. Its classification as a barred spiral, more specifically SBB, came after detailed plate studies showed the bright linear bar structure at its core and the sweeping spiral arms flaring outward. The real leap in understanding came with the space age, when the galaxy became a target for both ground-based and orbital observatories. Radio telescopes, such as those at the Parkes Observatory in Australia, mapped its hydrogen gas distribution, detecting vast reservoirs that traced the arcs of its spiral arms far beyond the bright stellar disk. These radio maps were essential for confirming the galaxy's extraordinary scale. Its gaseous disk was revealed to be even more extended than the distribution of visible stars. Observations in the infrared, such as those from the IRA satellite in the 1980s and later from the Spitzer Space Telescope, highlighted regions of intense star formation hidden within the dust lanes, especially in the tidal arms where gravitational forces from its companion galaxy, IC 4970, have triggered bursts of stellar birth. The Hubble Space Telescope's turn at imaging the Condor Galaxy produced some of the most striking views ever obtained. While Hubble's relatively narrow field of view could not capture the galaxy in its entirety without mosaicing multiple exposures, the telescope's sharp resolution allowed astronomers to examine individual star clusters and giant nebulae within the spiral arms. Young, massive clusters glittered like blue-white jewels, embedded in swirling streams of dust and gas, while dust lanes appeared as sharp, dark filigree cutting across the glowing background. Hubble's images confirmed that star formation is occurring on an immense scale, particularly in the outer regions that have been disturbed by its gravitational encounter. Other instruments expanded the picture. The Galaxy Space Telescope, working in ultraviolet light, revealed a halo of hot young stars extending far beyond the bright central regions, giving further evidence that the galaxy's outer arms are still actively forming stars despite their enormous distance from the nucleus. The Chandra X-ray Observatory found a scattering of bright X-ray sources, some of them likely to be ultraluminous X-ray binaries, systems where a black hole or neutron star is accreting matter from a companion. These X-ray hotspots hint at the population of massive stars that have already lived out their lives and collapsed into compact remnants. The Atacama Large Millimeter, Submillimeter Array, ALMA, in Chile, contributed critical detail about the galaxy's cold molecular gas, the raw material for star formation. ALMA's maps traced dense clouds in the spiral arms and along the tidal features connecting NGC 6872 to IC 4970, showing how these reservoirs are compressed during the interaction and collapse to form new generations of stars. These millimeter wavelength views complement the optical and ultraviolet data, giving a complete picture of the galaxy's life cycle. Cold clouds condensing into hot, young stars, which then burn brilliantly and end in supernova explosions, enriching the surrounding medium. Amateur astronomers, too, have played a role in keeping the Condor Galaxy in the public eye. With modern CCD cameras and long exposures, backyard observatories under dark skies can capture the galaxy's elongated form, though its fine details remain faint compared to brighter, closer spirals. For the dedicated astrophotographer, it remains a prized challenge, its beauty emerging from careful imaging and processing, revealing hints of the tidal distortions and faint extensions that make it so distinctive. Over the decades, the accumulation of these observations has transformed NGC 6872 from an obscure smudge in early photographic plates to a celebrated example of galactic extremes. Every wavelength studied, radio, infrared, optical, ultraviolet, and X-ray, has added a layer of understanding, showing a galaxy in dynamic evolution, shaped by both internal processes and external interactions. Its place in the astronomical record is now secure as the largest known barred spiral galaxy, a title supported not only by direct measurement, but by the collective scrutiny of generations of observers and instruments. The story of its discovery and subsequent study is, in many ways, a microcosm of modern astronomy itself, a journey from hazy suspicion to high-definition revelation, driven by the relentless advance of technology and the human urge to know the cosmos in ever greater detail. The story of when the Condor Galaxy and IC 4970 first began their cosmic dance is one that astronomers have pieced together through a mix of deep observations, simulations, and a good deal of forensic work. This is not a simple matter of looking at them and guessing when it all started. The universe doesn't leave behind a neatly labeled calendar. Instead, scientists reconstruct the timeline by studying the positions of stars, the shapes of galactic arms, the stretching of dust lanes, and even the speed at which certain regions are moving away or toward us. By layering all this data together, a picture emerges of two galaxies that have been engaged in a slow, graceful, but ultimately dramatic gravitational encounter for tens of millions of years. One of the key tools in figuring out this interaction's age has been computer simulations. These models take into account the mass of both the Condor and IC 4970, their relative velocities, their distances, and the physical laws governing how galaxies behave when gravity starts pulling them together. By tweaking these variables until the simulation produces a galaxy shape identical to what we see today in telescope images, astronomers can essentially rewind the cosmic clock. When they run this backward, they consistently find that the first close pass, the moment when IC 4970 came near enough to tug strongly at the Condor's stars and gas, likely happened somewhere between 130 and 200 million years ago. This range is broad, and that's because the timing of a galactic interaction depends on more than just the closest approach. Galaxies can start feeling each other's pull long before they make their nearest pass, and their structures can keep changing long afterward. In the case of the Condor, its enormous size and relatively slow rotation mean that the ripples from IC 4970's gravitational tug take a long time to propagate across its spiral arms. Even today, some of those waves of distortion are still moving outward, like ripples in a pond long after the stone has hit the water. That makes pinning down an exact date tricky. Astronomers have to distinguish between features formed right after the first pass and those created later in the encounter. The initial stages of the interaction may have been subtle, with only faint tidal streams beginning to form. As IC 4970 drifted closer, its compact shape allowed it to act like a gravitational anchor, pulling slightly more on one side of the Condor than the other. Over millions of years, this uneven force began stretching one of the spiral arms far beyond its original limits, giving the Condor its distinctive, elongated wingspan that now measures over 500,000 light-years. This massive feature did not appear overnight. It's the cumulative result of countless small shifts in the orbits of billions of stars, all coordinated by the relentless pull of gravity. When IC 4970 finally made its closest approach, likely a glancing pass rather than a head-on collision, the results were spectacular. Stars were thrown into new paths, gas clouds were compressed, and bursts of star formation erupted in certain regions of the Condor's arms. These starburst regions are like cosmic timestamps because their young hot stars live short lives. By measuring the ages of these stars, astronomers can estimate how long ago the bursts began, which in turn gives clues about when the closest approach occurred. Many of these stellar populations seem to have formed around 130 million years ago, which lines up neatly with the simulation's results. However, this was not a one-time event. In a gravitational encounter, galaxies often loop around each other in slow-motion spirals before parting ways or eventually merging. Some models suggest that IC 4970 may have made more than one close pass by the Condor, with the first being the most dramatic. Each pass would have further warped the Condor's structure, pulling its spiral arms into even more exaggerated shapes and possibly fueling additional waves of star formation. This could explain why some star-forming regions in the Condor appear younger than 100 million years. They might be the result of a later, secondary pass rather than the initial encounter. The space between galaxies is vast, but their mutual gravitational pull ensures that these dances last for hundreds of millions of years. Even though the Condor and IC 4970 are not physically colliding in the sense of solid objects smashing together, their stars are far too spread out for that. The overall gravitational influence is enough to transform both of them. IC 4970 itself has likely been stripped of some of its outer gas and dust during the interaction, while the Condor's sweeping wings have been stretched to record-breaking lengths. In the present day, the two galaxies are still close, and the gravitational connection between them hasn't yet been severed. Depending on their relative velocities, they might be on a path to eventually merge in the far future, although this would take hundreds of millions more years. For now, the Condor remains in a state of beautiful distortion, a living snapshot of an encounter that began when dinosaurs still walked the Earth. If we could somehow watch this process in real time, sped up over millions of years, we'd see IC 4970 swoop in, twist the Condor's arms outward, and then drift slightly away, while leaving the bigger galaxy structure forever altered. It's also worth noting that, from a cosmic perspective, the interaction between the Condor and IC 4970 is happening in slow motion. Every shift in the shape of its spiral arms takes millions of years to become noticeable. The tidal tails of stars and gas, long faint streams pulled out from the galaxy's edges, are reminders of the initial approach and continue to lengthen even now. These tidal tails may eventually dissipate into the surrounding intergalactic medium, but for the moment, they serve as a visual record of an ancient gravitational encounter. The current appearance of the Condor is, in a sense, a snapshot taken about halfway through this galactic ballet. The initial approach is long past. The arms are still settling into their new exaggerated forms, and IC 4970 remains nearby, still influencing the bigger galaxy's evolution. Astronomers studying this system today are, in effect, looking at a frozen moment in a very long and complex story, a story that began over 100 million years ago and will continue unfolding long after our own civilization is gone. Through simulations and observations, they've been able to reconstruct much of that story, but the exact details of the first encounter will always retain a hint of mystery, hidden in the vast and patient rhythms of the universe. If we peer far into the cosmic future, the story of the Condor Galaxy begins to take on a slow but dramatic transformation, a process that will unfold over billions of years. Right now, it is a magnificent barred spiral with two vast arms that stretch out like wings, the result of its earlier gravitational entanglement with its smaller companion, IC 4970. But like all galaxies, its appearance is not fixed in stone. Over time, gravity, dark matter dynamics, and the relentless process of galactic evolution will reshape it into something entirely different from the breathtaking form we see today. One of the most likely scenarios for its future begins with the lingering effects of the earlier encounter. Even though the Condor has already passed through the most visually striking phase of its collision with IC 4970, the gravitational aftershocks of that meeting will continue to ripple through its structure for hundreds of millions of years. Stars in its extended arms will gradually drift, the arms themselves winding more tightly as time passes, much like the unwinding of a cosmic clockwork that eventually slows. In the far reaches of its spiraling arms, some clusters may lose their gravitational grip on the galaxy altogether, becoming rogue star groups drifting into intergalactic space. Meanwhile, IC 4970 is unlikely to escape the Condor's pull entirely. It is small compared to the Condor, but still massive enough that its orbit is decaying over time. If the gravitational bond between them remains intact, astronomers predict that IC 4970 will eventually spiral inward and merge with the Condor. This won't be a head-on cataclysm, but rather a slow, drawn-out dance, possibly taking place over the next 1 to 2 billion years. Such a merger would send waves of disruption through the Condor's structure, distorting its elegant arms and scattering dust and gas into chaotic new shapes. It might trigger a final, brilliant burst of star formation, as the infalling gas clouds from IC 4970 collide with those already present in the Condor, compressing and igniting them into stellar nurseries. Over the course of the next several billion years, the Condor will also face the universal reality of aging stars and dwindling fuel. Even without further major collisions, the galaxy's gas reserves will be steadily depleted as new stars are born and old ones die. When the gas runs low, the rate of star formation will plummet. The Condor's once bright arms, glowing with blue-white light from massive young stars, will gradually take on a redder hue as older, cooler stars dominate the scene. The galaxy will enter a quieter, less active phase, what astronomers call a red and dead state, where most of the visible light comes from aging stars rather than vigorous star-forming regions. But the Condor's destiny may not be shaped only by IC 4970. In the vast timescale of the universe, no galaxy exists in isolation forever. The Condor lies within the Pavo-Indus supercluster, a region that contains other massive galaxies. Gravity will eventually draw many of these systems together, and large-scale mergers could dramatically transform the Condor's identity. Perhaps it will be pulled into a chain of collisions, growing larger with each encounter. Over a span of 5 to 10 billion years, it could be entirely remade into a giant elliptical galaxy, a type of galaxy that typically results from the merger of many spirals over cosmic time. If this happens, the graceful wings of the Condor will vanish. The ordered spiral structure will dissolve into a more featureless, rounded form. Any remaining gas and dust will either be consumed in rapid bursts of star formation triggered by the mergers, or expelled into intergalactic space by supernova explosions and the activity of central black holes. By then, the galaxy's supermassive black hole at its core, already a dominant feature, could grow much larger as it consumes infalling material during these interactions, possibly becoming one of the most massive black holes in its region of space. There is also the possibility that the Condor could find itself in a quieter cosmic environment for a while, avoiding major collisions for billions of years. In this case, it would age gracefully, slowly fading as its stars burn out. Massive stars would vanish first, followed by less massive ones over eons, until the galaxy's glow is made up primarily of long-lived, dim red dwarfs. This slower decline would still eventually erase the bright, youthful vibrancy of the Condor, replacing it with a subdued, ancient appearance. In the farthest reaches of time, trillions of years from now, when the universe itself will be drastically different, the Condor will no longer resemble anything like the grand spiral we see today. If it has merged with other galaxies, it might be part of a huge, nearly inert elliptical giant, its stars separated by vast dark stretches. Or, if it somehow remained more isolated, it could become a faint, ghostly spiral, barely lit by the dwindling energy of its last stars. The beauty we witness in the Condor today is, in cosmic terms, a fleeting moment. The tidal arms will tighten and fade, the central bar may weaken, and its symmetry will eventually be broken by the gravitational whims of its neighbors. Whether through slow aging or violent mergers, the Condor's future will be a transformation, perhaps into something even grander, perhaps into something quieter and more subdued. But no matter its fate, the galaxy's story is one of motion, change, and evolution on a scale that humbles human lifetimes. And somewhere deep in that story, its wings, forged in the chaos of past interactions, will remain a symbol of the ever-changing, ever-dancing universe, a reminder that even the largest structures in the cosmos are only temporary sculptures in the flow of time. Few galaxies in the universe manage to reach the extreme proportions of the Condor Galaxy, while still wearing the elegant, unmistakable spiral form that makes such galaxies so visually striking. In fact, the Condor isn't just large, it's a genuine outlier in multiple ways. Most spiral galaxies, especially those that grow to significant sizes, tend to lose their sharp spiral definition over cosmic time. Interactions with neighboring galaxies, repeated mergers, and gravitational disturbances from satellite companions often distort, warp, or erase their classic spiral arms. What you end up with in most giant systems is not a neat, symmetrical disk, but rather an irregular or lenticular shape, or a massive elliptical galaxy which lacks any spiral arms at all. Yet somehow, the Condor has defied these odds, stretching its grand arms out for over 500,000 light-years and still keeping them recognizable as part of a spiral design. This rarity comes from several interconnected astrophysical constraints. Spiral galaxies form and maintain their iconic arms because of a delicate balance between rotational motion, density waves, star formation, and gravitational stability. The more massive a spiral galaxy becomes, the harder it is to keep that balance intact. Gigantic spirals tend to suffer from instability in their disks, where differential rotation causes material to shear apart, smearing out arms. If the galaxy has undergone significant mergers, these events typically flood the system with random stellar orbits, diluting the disk structure and leading to a more spheroidal or elliptical shape. The fact that the Condor has kept such symmetry means it has had a relatively unusual evolutionary history compared to other massive galaxies. Astronomers often note that in the local universe, there's a size ceiling for spirals. The Milky Way, at around 100,000 light-years across, is already considered large. Andromeda pushes the limit further at around 220,000 light-years when counting faint outer disk features. But the Condor, at more than twice Andromeda's scale, blows past this boundary. Such dimensions are almost never seen without structural collapse into something more irregular. This makes it a textbook case of rarity, not simply because of size, but because of what that size represents in terms of galactic dynamics. One reason why spirals this vast are uncommon has to do with angular momentum distribution during galaxy formation. To grow to this extent, the original proto-galactic cloud must have had an unusually large amount of angular momentum, spinning fast enough to spread material out over such an enormous area without causing the disk to fragment under its own gravity. At the same time, it had to avoid excessive interactions that would have scrambled the rotation. That combination is already statistically rare. Now add the requirement that over billions of years, the spiral arms must remain distinct rather than being shredded by tidal forces, and you end up with a truly exceptional cosmic survivor. Another factor is the environmental challenge. Large spiral galaxies are particularly vulnerable to their surroundings. If they exist in dense galaxy clusters, gravitational harassment from multiple neighbors tends to distort them beyond recognition. Even a single close pass by a comparably massive galaxy can be enough to erase or severely warp the arms. The Condor, however, lives in a group environment that has given it enough room to grow without being constantly battered by larger companions. That's not to say it has been untouched. The interaction with IC 4970 clearly shows that it's experienced close encounters. But these interactions haven't been catastrophic enough to strip away its spiral essence. This delicate balance between disturbance and preservation is extremely rare for a galaxy of its scale. What also sets the Condor apart is the visibility of its arms. In most supergiant spirals, the outer arms become so faint and diffuse that they are difficult to detect, even with powerful telescopes. In contrast, the Condor's sweeping arms remain relatively coherent, with star-forming regions and stellar streams tracing graceful arcs far into intergalactic space. This suggests that the disk's density waves, the patterns that define spiral arms, are still strong enough to gather gas and dust into structured lanes. Maintaining such defined arms at this size implies that the galaxy's internal dynamics are remarkably stable, another rarity in the universe. The scarcity of similar systems also ties into cosmic timescales. In the early universe, spiral galaxies were far more chaotic, and massive mergers were frequent, making large, symmetrical spirals essentially impossible to sustain. As the universe aged and the frequency of major collisions declined, spirals became more common, but not at this scale. By the time galaxies could grow this large in a relatively peaceful environment, the conditions needed to form one had already become highly selective. The Condor, therefore, is a product of both extraordinary luck and a unique cosmic context, existing in a narrow window where size and stability could coincide. For astronomers, the rarity of the Condor has observational consequences. Since there are so few galaxies of comparable size and structure, each one becomes an important laboratory for testing models of galaxy formation and evolution. It's not enough to explain why spirals form. Scientists must also account for why only a handful of them can stretch this far without losing their identity. The Condor offers clues in its mass distribution, star formation patterns, and history of interactions, but it also raises new questions. Could there be even larger spirals hiding at greater distances, whose faint outer arms are simply beyond current detection limits? Or is the Condor truly pushing the physical limits of what a spiral galaxy can be before it transitions into something else entirely? Ultimately, the rarity of galaxies like the Condor underscores just how finely tuned the universe's processes can be. In a cosmos filled with billions of galaxies, it's easy to assume that there's a huge variety of every type. But certain combinations, like immense size paired with spiral perfection, are exceptions rather than rules. The Condor is one of those cosmic exceptions, a rare alignment of conditions, history, and physics that has allowed it to stand out as both a giant and a beauty. The fact that it exists at all makes it an astronomical treasure, not just because of what we see when we look at it, but because of what it tells us about how rare and precious certain cosmic arrangements truly are. NGC 6872 offers astronomers a unique laboratory for studying the dynamics, mechanics, and consequences of galactic collisions on a truly grand scale. Its sheer size, over 500,000 light-years across, means that the physical processes shaping it are stretched out over vast distances, allowing scientists to observe them in ways that aren't always possible in smaller or more compact merging galaxies. This enormous scale acts almost like a slow-motion replay of a collision in progress. The gravitational pull between NGC 6872 and its smaller companion galaxy, IC 4970, has created tidal forces that have warped and elongated the spiral arms of NGC 6872 far beyond their typical bounds, giving researchers a direct view of how gravitational interactions redistribute stars, gas, and dust over cosmic timescales. By mapping the distribution of stars across its distorted arms, astronomers can trace the history of the interaction, determining which parts of the galaxy were pulled outward first, how quickly the material is moving, and how far the gravitational influence of a smaller galaxy can extend into a larger one. These tidal tails, brimming with newly formed stars, demonstrate one of the key effects of galactic encounters: the ability to compress interstellar gas and trigger intense bursts of star formation. In NGC 6872, the regions of brightest young stars are often far from the galactic core, illustrating that collisions do not just ignite activity in a galaxy's central regions, but can stimulate starbirth in its farthest reaches. This is an important finding because it challenges older models that emphasized central starbursts as the main signature of galactic mergers. Studying NGC 6872 also sheds light on the early history of the universe. Billions of years ago, galactic collisions were far more common because galaxies were closer together in the denser young cosmos. Observing a collision in our relatively nearby universe allows astronomers to build detailed models and simulations that can then be applied to understanding ancient mergers at far greater distances, objects that are too faint or too small in angular size to study in such detail. NGC 6872's current interaction with IC 4970 mirrors, in some ways, the processes that helped assemble the massive galaxies we see today, meaning it's essentially a time machine showing us the building blocks of cosmic structure. Another crucial aspect is the way NGC 6872 reveals how galactic collisions redistribute angular momentum. In normal spiral galaxies, stars and gas move in relatively ordered, predictable orbits. But when a smaller galaxy interacts with a larger one, gravitational forces can sling some material outward while pulling other material inward, disrupting these orderly motions. Over time, this can transform the galaxy's shape, from spiral to elliptical, or lead to the growth of massive central bulges. NGC 6872 is currently still a spiral, but simulations based on its structure suggest that repeated or prolonged encounters could eventually strip away its arms or cause them to collapse inward, signaling the transitional phase that leads to a more elliptical form. This transitional nature makes it a key object for testing theories of galactic evolution. Additionally, the galaxy provides insights into the role of dark matter in galactic interactions. The way NGC 6872's outer arms remain gravitationally bound despite their extreme length suggests the presence of an extensive dark matter halo that helps hold the system together. By comparing the observed motions of stars and gas to what would be expected from visible matter alone, astronomers can estimate the size and distribution of dark matter around the galaxy. Understanding this relationship is vital because dark matter dominates the mass of galaxies and plays a decisive role in shaping their interactions and eventual fate. Gas dynamics in NGC 6872 are another field of study with high scientific importance. The collision with IC 4970 has rearranged large reservoirs of neutral hydrogen gas, pushing it into dense knots that serve as cradles for new stars. Astronomers using radio telescopes have mapped these hydrogen streams, finding that some extend tens of thousands of light years beyond the visible stellar disk. These long, thin filaments act as evidence of the invisible gravitational tug-of-war between the galaxies and help researchers determine the exact trajectory and velocity of the companion galaxy during the interaction. In some cases, the stripped gas could even escape entirely, feeding the intergalactic medium and enriching it with heavier elements produced by stars. The ultraviolet and infrared observations of NGC 6872 add another layer to its importance. Ultraviolet imaging reveals regions of active young star clusters, while infrared data shows where dust, heated by those same young stars, is concentrated. This combination allows astronomers to piece together a timeline of star formation, estimating how long ago various regions were disturbed by the collision. It also helps identify which parts of the galaxy are experiencing the most intense growth and which are quiescent, offering clues about how star formation propagates after a galactic encounter. The pattern of star formation in NGC 6872 suggests that these events can proceed in waves, triggered first in one region and then in another as shock fronts travel through the galaxy's spiral arms. Beyond its local scientific impact, NGC 6872 is important for refining computer models of galactic mergers. Simulations of galactic collisions are only as good as the real-world data used to validate them, and NGC 6872 provides an exceptionally detailed and large-scale example. By matching observed structures, like the length and curvature of its arms, the position of star-forming knots, and the velocity distribution of its stars, to simulated scenarios, astronomers can test different collision angles, speeds, and mass ratios. This iterative process improves our ability to reconstruct the histories of other, more distant merging galaxies that cannot be studied as closely. In the bigger picture, NGC 6872 also contributes to our understanding of how galaxies recycle and transform their material. Collisions can strip gas from one galaxy and feed it into another, or they can fling it into intergalactic space, where it may later fall back into a galaxy. This constant circulation of matter not only shapes the galaxies themselves, but also affects the larger cosmic web in which they are embedded. Studying the extreme case of NGC 6872 allows scientists to see how such recycling operates when a galaxy's structure is pushed to its limits. Even the future fate of NGC 6872 offers lessons. It is likely that the current interaction will not be the last. Over hundreds of millions of years, gravitational attraction may pull IC 4970 into a full merger with NGC 6872, eventually producing a single, larger galaxy. Observing its current stage gives astronomers a before snapshot that can be compared to the after state in future epochs or in analogous systems that are further along in the merging process. This long-term perspective is invaluable for understanding the complete life cycle of galaxies. Every observation of NGC 6872, whether in visible light, radio waves, infrared, or ultraviolet, adds to a growing mosaic of knowledge about how cosmic structures form, interact, and change. Its massive scale, dramatic tidal features, and active star-forming regions make it a benchmark object for collision physics and galactic evolution theory. In essence, NGC 6872 is not just a galaxy, it is a vast cosmic experiment in progress, one that nature has been running for hundreds of millions of years, and which humanity has the rare privilege of observing in remarkable detail. By continuing to study it, astronomers gain not just insights into this single extraordinary galaxy, but also a deeper understanding of the forces that have shaped, and will continue to shape, the universe itself. As the gaze travels across the expanse of the Condor Galaxy, it becomes impossible not to be enveloped by a sense of cosmic wonder, a quiet reverence for a structure that simultaneously embodies both immense power and delicate elegance. Its spiral arms, extending over 500,000 light-years, do not merely stretch across space. They soar, curling outward like the wings of a cosmic bird gliding silently through the void. Each arm is a narrative of gravitational forces and celestial evolution, carrying within it regions of furious star formation, clusters of brilliant blue stars, and streaks of gas and dust that weave together a story billions of years in the making. The Condor is alive with motion, a dance of matter orchestrated by the invisible hand of gravity, yet it moves with a grace that transforms these immense forces into a visual poetry that transcends human comprehension. The contrast within the galaxy adds depth to its majesty. Its central bar anchors the system, a robust spine of older reddish stars that have existed for billions of years, guiding the flow of interstellar material inward and fueling a slower, steadier pace of star formation near the core. In the outer arms, brilliant blue star-forming regions flash like jewels at the tips, a dazzling display of youthful energy set against the dark canvas of space. These colors and textures, though captured from light that has traveled for hundreds of thousands of years, paint a vivid portrait of the life and vitality inherent in such a colossal structure. It is a place of contrasts, youth and age, turbulence and order, vast emptiness and dense clusters of stars, all coexisting in harmony. The scale of the Condor defies human intuition. To imagine its arms stretching farther than 5 Milky Ways is to confront a dimension that is almost inconceivable. Yet within this vastness, each star, each cloud of gas, and each cluster of newly formed suns is bound by the subtle but relentless laws of physics. This interplay between unimaginable size and precise mechanics is what makes the galaxy a masterpiece of natural design. It is a living reminder that the universe, though often violent and chaotic, has the capacity for beauty and balance on scales that dwarf our own existence. The poetic aspect of the Condor becomes even more pronounced when considering its motion. The galaxy is not frozen in space. Its arms spiral outward, density waves sweeping through its disk like the rhythm of a heartbeat, organizing stars, gas, and dust into coherent patterns. The gravitational tug from its companion, IC 4970, stretches these arms further, creating elongated tidal tails that ripple across the cosmic landscape. Even in these distortions, there is beauty, a testament to the resilience of the galaxy's spiral structure, a sign that even amid disturbance and disruption, elegance persists. There is also a philosophical dimension to this spectacle. Observing the Condor is to witness time itself rendered visible. The light reaching our telescopes today left the galaxy's distant reaches hundreds of thousands of years ago, long before humanity had even emerged as a species. Each photon carries with it a message from the past, a whisper of the galaxy's ongoing evolution. In this sense, the Condor is both a window into cosmic history and a mirror reflecting the fleeting nature of human existence against the backdrop of billions of years of galactic life. Its wings stretch across the void with an enduring presence, a silent chronicle of time, motion, and transformation. And yet, despite its colossal size and ancient history, the Condor is not a static monument. It is a living system, evolving as IC 4970 continues to orbit and interact with it, as stars are born and die, and as gas flows and coalesces under the influence of gravity. Its future is a canvas of possibilities. Spiral arms may wind tighter, new regions of star formation may ignite, and tidal forces may reshape its form. This constant evolution underscores the galaxy's vitality and emphasizes that cosmic beauty is dynamic, not fixed, written in the language of motion, gravity, and time. In the final reflection, the Condor Galaxy transcends the role of a mere astronomical object. It is a symbol of cosmic grandeur, of resilience amid interaction, and of the breathtaking scale and elegance that the universe can achieve. Its wings, vast, luminous, and intricately structured, invite the mind to soar alongside them, to appreciate the artistry inherent in natural law, and to contemplate the interconnectedness of all matter across the cosmos. The galaxy is a living poem, a cosmic condor gliding silently through the intergalactic void, carrying with it the tales of creation, collision, and the unending cycle of stellar life. Its beauty is both humbling and inspiring, a reminder that even in the infinite expanse of space, there are singular marvels whose presence invites awe, reflection, and a profound sense of wonder at the universe we inhabit. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.